Alright, boys and girls, welcome back for another remix, a double remix of this day. This is number 25 from 12-4, sponsored by the deli. Hungry? Stop by the deli. Get yourself a Butterfinger again. Another Butterfinger. Alright, here we go. We're trying to explain the difference between dA and delta A here, okay? This is question 25. You'll see that I'm going to fill in a couple things here. You're given a rectangle whose area is LH. That's the shaded rectangle right there. Okay. You also know that you've got this delta H and delta L, and those are possible errors in the length in your measurement. Okay. You want to identify dA, okay, and then also figure out the difference between dA and delta A. Well, delta A, just geometrically, is going to be this white section. It's the change in area, okay? It's the big rectangle minus the small rectangle. To find delta A, we would take the big rectangle, take its area, and subtract out the yellow rectangle's area. So we're going to have to do some foiling to do that. So delta A is going to represent our error. Awkward pause. I think at this point I'm maybe giving bad looks to Josh. Okay. Nothing. So, look, our error in measurement is going to be our big area, our big rectangle, minus our little rectangle. So notice, our big area is that foiling thing, and our small area is just H times L. So here I'll foil it out for you. Awkward pause. And you get HL plus H delta L plus delta HL plus delta H delta L. And then we're going to subtract out our yellow area so we can just find the error in measurement, and we get HL. We could do that every time if we wanted, and that would find our actual error in measurement, okay? It's H delta L plus delta HL plus delta H delta L. Now let's compare that to dA. Remember that dA is the total differential of the area. It's, by definition, it is the partial derivative with respect to L times dL plus the partial derivative with respect to H times dH. Okay, well, the derivative with this respect to L is H. Do you understand that? The derivative of LH with respect to L is just H. And then you multiply it by dL. And you're going to add the derivative of LH with respect to H, and that's just going to be L. It's just a constant. So then it'll be L dH. Well, look, if we consider delta H to be dH and delta L to be dL, then dA is represented by those little black shaded areas there. So what is the difference between delta A and dA? That pink little cube right there. That's the only difference. Okay? So, the question becomes, why are we learning these total differentials? What is the point of all this? Alright, well, the point is that eventually these equations will not be so easy to represent geometrically. They might be in 7 dimensions or 10 dimensions. And all that means is they might have 9 variables, okay? Now, we just had 2 variables, H and L, and we had to FOIL it out. And that foiling process is natural to us, and it comes pretty easy. But keep in mind, if we had 3 variables, then we would have to FOIL a trinomial, kind of, you know? And it's just going to get really ugly. And why would we do that if we have a very good way to approximate it using calculus? So that's what we're doing. The total differential is an approximation of error, but it's something that's very simple, like right here. And we could pop that into a computer and get the answer out real quick. It's a simple process, okay? And that is the advantage. That's it. That's why we're doing this. Boom!